Two spacecraft called Voyager, launched in 1977, built to last 5 years, are still flying today, nearly 50 years later. And the discoveries they made at the edge of our solar system proved that humanity's best science had been wrong about our own cosmic home. Today we follow Voyager's journey to the boundary of everything we know and find out how wrong we were. Let's begin. In 2013, a NASA engineer sat in front of a screen and realized something that stopped him cold. A spacecraft they had long assumed was running on borrowed time, a machine launched before personal computers existed, before the internet existed, before most people in that room were born, was still sending data back. Clean data, detailed data, from a place no human-made object had ever reached before. It wasn't a system glitch. It wasn't signal interference. It wasn't a software ghost echoing old transmissions through deep space. Voyager 1 was in actual interstellar space, and it was reporting back on conditions that turned everything the scientific community thought it understood completely upside down. That alone would have been enough to silence a room. But then came the second shock, almost immediately. The spacecraft doing all of this was running on 68 kilobytes of memory. Not megabytes, not gigabytes. 68 kilobytes less than what your cheapest smartphone in 2024 needs to store a single photo taken in a dimly lit room. The machine rewriting humanity's understanding of its own cosmic neighborhood couldn't hold one picture of it. And then the third shock, which might be the strangest of all, the signal Voyager 1 was sending home, that stream of data crossing billions of kilometers of empty space, arrived at Earth's antennas carrying the power of 1 femtowatt. 1 quadrillionth of a watt. To put that in perspective, a single LED nightlight uses roughly 1 billion times more power than the signal Voyager 1 sends from the edge of known space. And yet NASA's Deep Space Network could read every single bit of it. Not approximately. Exactly. Think about what that means for a moment. Inside the mission control room, when the confirmation finally came through in September 2013, there was no immediate celebration, no applause. No one jumped out of their chair. Scientists who had spent decades studying the boundary of the solar system sat quietly with their data, because the data wasn't saying what any of them had expected it to say. Voyager 1 had crossed the heliopause, the outermost boundary, where the sun's influence ends and true interstellar space begins at 121 astronomical units from the sun. 1 astronomical unit is the distance from Earth to the sun, roughly 150 million kilometers. So, 121 of those. The scientific community had predicted with considerable confidence, built on decades of modeling, that this boundary would sit somewhere around 90 to 100 astronomical units, not a rough guess. A careful, mathematically rigorous prediction run through sophisticated computer simulations, peer-reviewed, refined, and generally agreed upon across the field. Voyager 1 crossed it more than 4 billion kilometers past where everyone had placed their bets. 4 billion kilometers. That's not a rounding error. That's not within the margin of uncertainty. That's the kind of gap between prediction and reality that forces scientists to go back to the very beginning and ask which assumption was wrong and how confident they should be about the ones they haven't tested yet. Here is what made this discovery simultaneously humbling and magnificent. Voyager 1 didn't do anything miraculous. It didn't malfunction in a useful direction. It didn't discover some hidden propulsion. It simply flew in a straight line as it had been flying for 35 years and reported honestly what it found when it got there. The universe was the one that refused to cooperate. The universe didn't care about the models. It didn't care about the simulations, the peer-reviewed papers, or the textbooks, already printed with diagrams showing a neat spherical boundary at a predictable distance. The solar system's edge was where it was, not where the equations said it should be. And the data coming back from Voyager 1 wasn't just wrong about the distance, it was wrong about the shape, wrong about how the boundary behaved, wrong about what the space beyond it actually looked like. 7 major discoveries, each one a place where reality walked away from the prediction. But sit with the broader question for a moment, because it matters more than any single measurement. The heliopause is the boundary of our own solar system, the system we live in. The system we've been observing for centuries, with increasingly powerful instruments, modeling with increasingly powerful computers, and studying with probes, satellites, and telescopes pointed in every direction. If our best science, our most rigorous, best funded, most carefully constructed understanding, was off by 4 billion kilometers about where our own home ends, what else are we getting wrong? Not in a way that undermines science, quite the opposite. In a way that reveals exactly what science is actually for. The models weren't built by careless people. The predictions weren't made by bad scientists. They were made by brilliant people working with the best available data, and they were still wrong because the best available data wasn't good enough. Because measuring something from a distance and measuring it up close are two entirely different things. Because the universe has a way of holding its most interesting details until you actually show up. That's the story Voyager 1 is really telling. Not that we were foolish, but that we were finally close enough to find out the truth. If the universe keeps breaking science's predictions, does that make you trust science more or less? But to understand why this shock hit as hard as it did, you need to know how confident scientists really were, and where that confidence came from. Confidence in science is rarely reckless. It's usually earned step by step through tests that work and predictions that hold. And by the 1980s and 1990s, the scientific community had very good reasons to feel confident about where the edge of the solar system should be. The models predicting the heliopause at 90 to 100 astronomical units weren't back-of-the-envelope calculations. They were the product of full three-dimensional magnetohydrodynamic simulations, computational models that account for the behavior of electrically charged gas moving through magnetic fields, running on the most powerful supercomputers available at the time. The results converged consistently. Different research groups, different models, different assumptions about secondary variables, and they all kept pointing to the same general answer. That kind of consistency feels like confirmation. And the physics underlying those models wasn't speculative. The equations governing plasma behavior had been tested for decades, in environments far more controlled than outer space, in fusion reactor experiments, in particle accelerator facilities, in magnetic confinement chambers. They worked. They were accurate. They predicted plasma behavior in terrestrial conditions with remarkable precision. So when scientists applied those same equations to the problem of solar wind meeting interstellar gas, they had every reason to believe the output. The solar wind measurements near Earth were particularly solid. Satellites and space probes stationed in the inner solar system had been measuring the solar wind for years. Its speed, its density, its composition, the strength of the magnetic field it carried. The data was detailed, consistent, and reliable. Scientists knew exactly how hard the sun was blowing. The logic was straightforward. You know the pressure pushing outward the solar wind. You know the pressure pushing inward the interstellar medium pressing against the boundary from outside. Find the point where they balance, and that's where the heliopause sits. The first measurement was solid. The second was the problem, and no one recognized it as a problem because no one had a better option. The density of the interstellar medium, the thin gas filling the space between stars, was estimated from astronomical observations, telescopes watching the light from distant stars as it passed through interstellar gas. Spectroscopic readings of absorption lines, indicating the chemical composition and rough density of the medium along various lines of sight. It was careful work. It was the best available method. And it produced estimates that seemed reasonable, consistent with other data, and generally agreed upon across the field. The lethal assumption, hidden inside all of this, was invisible precisely because it seemed so reasonable. Those estimates were measuring the interstellar medium remotely from Earth through light that had traveled thousands of light years. Before arriving at the telescope, every layer of space that light passed through left a subtle imprint on the signal. Every interaction along the way introduced a small distortion. The cumulative effect of all those small distortions on the final density estimate was something nobody had a reliable way to calculate. The result, the interstellar medium, turned out to be somewhat less dense than the models assumed. Not dramatically less. Not by an order of magnitude, just a few tens of % lower than the estimates. In everyday terms, a few tens of percent sounds like a small error. In terms of the force balance between solar wind and interstellar pressure, a balance being struck billions of kilometers from the sun, a few tens of percent in the wrong direction was enough to push the equilibrium point outward by more than 4 billion kilometers. Small input error. Enormous output consequence. That's not a failure of intelligence. That's the mathematics of extrapolation across vast distances. There was something else nobody had fully appreciated until Voyager actually arrived. The heliosphere wasn't a static bubble sitting quietly at a fixed distance waiting to be measured. It was breathing. When the sun becomes more active, producing stronger solar wind through increased magnetic activity and eruptions, the added outward pressure pushes the boundary farther from the sun. When the sun quiets down, the boundary contracts inward. The heliopause moves. Not slowly over years, but dynamically in response to individual solar events, shifting outward and inward by significant distances on timescales far shorter than anyone had modeled. This means that asking how far away is the heliopause is a little like asking how tall is the ocean. The answer depends entirely on when and where you measure. No model in the 1980s or 1990s fully captured this. The models treated the boundary as roughly stable, perhaps drifting slowly with the 11-year solar cycle. They didn't account for a boundary that could surge outward after a large solar storm and then contract again weeks later. They didn't account for the possibility that a spacecraft could cross the boundary, then find itself back inside the heliosphere as the boundary expanded past it again, then cross once more as it contracted. That is exactly what happened to Voyager 1. The boundary crossed it multiple times before it finally stayed on the interstellar side for good. The lesson here isn't that scientists were sloppy. It's that measuring something from a distance and measuring it in person are two fundamentally different kinds of knowledge. Humanity had been studying the edge of the solar system the way you study a coastline from an airplane, able to see the general shape, the approximate location, the broad outlines. What Voyager found when it actually reached the shore was that the coastline was in a completely different place, had a completely different shape, and was moving in ways the aerial view couldn't have shown. Basically, humanity spent decades using telescopes from one side of the planet to draw a detailed map of the other side, and then seemed surprised when the map was wrong once someone actually got there. Did science get it wrong because of bad methods, or simply because it didn't yet have enough data? And how are those two things different from each other? But to send something all the way out there and measure it directly, NASA had to wait for an astronomical event that only happens once every 176 years. And that window was closing fast. In 1964, a young aerospace engineer named Gary Flandreau was working at NASA's Jet Propulsion Laboratory on what seemed like a routine orbital calculation assignment. He was asked to look into possible trajectories for future outer planet missions. What he found in his calculations stopped him completely. In 1977, Jupiter, Saturn, Uranus, and Neptune would align along an arc of their orbits that occurs once every 176 years. Not a straight line, an arc. A specific geometric arrangement that would allow a spacecraft to fly from one planet to the next, using each planet's gravity to accelerate toward the next target, like a chain of slingshots laid out across the outer solar system. The next time this alignment would occur after 1977, the year 2153, nobody in that room in 1964 would be alive to see it. Nobody's children would be alive to see it. If NASA didn't launch in 1977, the entire concept of a grand tour of the outer planets would have to be handed down like an unfinished letter across generations to scientists not yet born. The window was open. It would not open again for anyone currently breathing. To understand why this alignment mattered so much, you need to understand what gravity assist actually is, because the popular description of planets pulling spacecraft faster gets it subtly but importantly wrong. A spacecraft approaching a planet doesn't just get pulled toward it and sped up. What actually happens is more elegant than that. The spacecraft flies a curved path around the backside of a planet that is itself moving through space. By swinging around behind the planet in its direction of travel, the spacecraft effectively borrows a fraction of the planet's own orbital momentum. The planet is so incomparably massive that the tiny amount of momentum transferred to the spacecraft slows the planet down by an amount so small it cannot be measured with any instrument. But for the spacecraft that borrowed momentum, translates into a significant velocity increase without burning a single drop of additional fuel. Energy is conserved perfectly. Nothing is created from nothing. The spacecraft gains speed at the precise expense of the planet's orbital energy in an amount too small to ever detect, but real nonetheless. It is gravitational mechanics working exactly as the equations describe, producing something that feels almost like getting something for free. Without this technique, sending a spacecraft to all 4 outer planets in a single mission would have required carrying so much fuel that no rocket ever built could have lifted it off the ground. With it, a relatively modest spacecraft could travel from Jupiter to Saturn to Uranus to Neptune on a single tank, using the solar system's own architecture as its propulsion system. Flandreau's calculation didn't just identify an opportunity. It identified the only opportunity anyone alive would ever have. The pressure that created put a particular kind of weight on the engineers building the spacecraft. They had a few years to design and construct machines that would need to survive a journey no spacecraft had ever attempted. The budget was real but not unlimited. The technology available was what existed in the early 1970s. No digital cameras, no modern microprocessors, no solid-state memory beyond a few kilobytes. Everything had to be designed, built, tested, and ready to launch by August of 1977. And here was the deeper constraint: nobody actually expected the mission to last only 5 years, even though that was the official design lifetime. The planets would be visited in 5 years. But after that, if the spacecraft kept working, they would continue outward, possibly far outward. The engineers building them understood, at least implicitly, that they might be building something that would outlast not just the mission, but their own careers, their own lives, perhaps even the institution that built them. That understanding shaped the most important design decision of the entire program: simplify everything. If a system doesn't need to be complex, make it simple. If a component can be over-engineered without adding weight or cost, over-engineer it. Build redundancy into every critical system. Choose components rated for loads beyond what the mission requires. Design for the unexpected, because anything that travels far enough will eventually encounter the unexpected. No elegant miniaturization that might fail in novel ways. No sophisticated mechanisms with many points of potential failure. Robust, redundant, conservative engineering, the kind that sacrifices elegance for durability. It was the right call, and it would be proven right in ways nobody could have anticipated at the time. Power was perhaps the most fundamental challenge. Beyond Mars, sunlight becomes too weak to run meaningful solar panels. By the time you reach Jupiter, sunlight is already 25 times weaker than at Earth. By Neptune, it is 900 times weaker. A solar-powered spacecraft in the outer solar system is essentially a spacecraft with no power. The solution was plutonium-238. Not the weapons-grade isotope, but a specific form of plutonium, chosen precisely because it decays at a steady, manageable rate, producing heat as it does. That heat is converted into electricity through thermoelectric generators. No moving parts, no combustion, no solar panels needed. Just the quiet, continuous decay of radioactive material, reliably producing power year after year after year. 2020. At launch, each spacecraft generated roughly 470 watts from these generators. Not much less than a typical household appliance, but enough to run the instruments and systems on board. The catch plutonium decays continuously. Output drops at roughly 4 watts per year. There is no way to slow this process. The power budget shrinks permanently every single year. The spacecraft were designed knowing this. Every instrument, every heater, every transmitter was prioritized against a power budget that could only decrease. Engineers in the 1970s were essentially writing a spending plan for a bank account that would drain by 4 watts per year forever, with no deposits ever possible. Voyager 2 launched first on August 20th, 1977. Voyager 1 followed on September 5th, 1977, 16 days later. And yet Voyager 1 reached Jupiter first because it was placed on a faster, more direct trajectory toward the inner targets. The names reflect arrival order at the destinations, not the order the spacecraft left Earth. It is a small but telling detail. Even the naming convention was designed around the mission's objectives, not its chronology. Each spacecraft carried a 3.7-meter diameter parabolic dish antenna, the single most critical piece of hardware on board in a certain sense. Not because of what it measured or recorded, but because it was the only thread connecting the spacecraft to the civilization that built it. Everything Voyager learned, everything it measured, everything it discovered across 47 years of travel, all of it had to fit through that antenna and travel home as a radio signal weaker than the light produced by a small nightlight. That signal would still arrive, still be readable, still carry meaning across distances that take light itself many hours to cross. Would you be willing to start a project knowing that its most important results would only arrive after you were gone? 2 spacecraft left Earth, and the first things they encountered were not the endless void. They were worlds that broke everything science thought it knew about our solar system. When Voyager 1 reached Jupiter in March of 1979, scientists were expecting to get a better look at a planet they already understood in broad terms. A massive gas world, a giant storm, a strong magnetic field, a few moons. They had seen Jupiter through Earth-based telescopes for centuries. They thought they knew what they were looking at. What Voyager sent back made it clear they had been looking at a postcard of a place they had never actually visited. Jupiter's atmosphere, seen up close for the first time, was not a simple system of bands and a single large storm. It was a planet-wide engine of staggering complexity, dozens of interacting storm systems, each one larger than most hurricanes on Earth, flowing in alternating bands of east and west winds, driven not by sunlight but by heat rising from deep inside the planet itself. Jupiter radiates more energy than it receives from the Sun. Its weather is powered from below, not above. The Sun is largely irrelevant to what happens in Jupiter's clouds. The Great Red Spot, the storm that had been visible from Earth since at least the 17th century, turned out to be an anticyclone, a high-pressure system rotating counterclockwise, rising above the surrounding cloud layers, and sustained by dynamics that no terrestrial weather system can fully mirror. It had been turning continuously for at least 350 years at the time Voyager flew past. It was wider than the entire Earth. And despite its age and scale, it was slowly shrinking, contracting over decades by a process that even today is not fully understood. Nobody could explain why it hadn't dissolved centuries ago. Nobody could fully explain why it was shrinking now. Then came Io, and Io was something else entirely. Io is smaller than Earth's moon. By size alone, it should be a cold, geologically dead rock, too small to retain the internal heat that drives volcanism on larger bodies. That is exactly what scientists expected to find. A cratered, frozen surface quiet for billions of years. Navigation engineer Linda Morabito was processing Voyager images to precisely determine the spacecraft's position, to routine work, not scientific analysis, when she noticed something unusual on the edge of Io in one of the frames. A faint umbrella-shaped plume extending above the moon's limb. She looked at it again, then called her colleagues. It was a volcanic eruption, the first active volcano ever discovered beyond Earth. Nobody was looking for it. Nobody had predicted it. It was found by accident in an image being used for navigation by an engineer doing position calculations. Io turned out to be the most volcanically active body in the entire solar system. Not because it has a hot core, its interior would have cooled long ago on its own, but because Jupiter's immense gravitational field combined with the gravitational pulls of the neighboring moons Europa and Ganymede constantly flexes and squeezes Io's interior as it moves through its orbit. That flexing generates friction. That friction generates heat, enough heat, to keep Io's interior partially molten enough to drive hundreds of active volcanic centers across its surface. Some of Io's volcanic plumes reach heights of nearly 300 kilometers above the surface. The mechanism was not invented for Io. The physics of tidal heating had been theorized before. But Io was the first place where anyone could actually see it at work, and seeing it changed how scientists think about energy sources for geological activity throughout the solar system and beyond. Europa, the next of Jupiter's large moons, told a completely different story, and in some ways a more consequential one. Its surface was ice. But the ice was fractured, long linear cracks running for hundreds of kilometers, curved ridges, regions where the surface appeared to have broken apart and refrozen in chaotic patterns, and almost no impact craters, virtually none. In planetary science, the density of impact craters on a surface is a clock. Old surfaces accumulate craters over billions of years. Young surfaces, ones that have been renewed recently, have few. Europa's surface was young, actively being resurfaced by processes happening beneath it. Beneath a shell of water ice, the same tidal heating that tears Io apart might be warming Europa's interior enough to keep liquid water stable, not on the surface where temperatures drop to around -160 degrees Celsius. But underneath, insulated by kilometers of ice above a liquid ocean, might persist deeper than any ocean on Earth, containing more liquid water than all of Earth's oceans combined, if the models are correct. Voyager couldn't prove the ocean existed, but it provided the first credible evidence that it might. And that possibility, a liquid water ocean beneath the ice of a moon 480 million miles from Earth, changed the entire conversation about where life in the solar system might exist. Saturn, reached by Voyager 1 in November of 1980 and Voyager 2 in August of 1981, delivered its own surprises. The rings visible from Earth since the 17th century, and known to be made of ice and rock, turned out to be vastly more structured than anyone had imagined. What looked from Earth like a few broad bands was actually thousands of individual ringlets, each one the product of gravitational interactions between ring particles and Saturn's many moons. Waves rippled through the rings, sharp edges maintained by tiny shepherd moons orbiting just inside and outside the ring boundaries. Spokes, dark radial features that rotated with the rings in ways that defied simple orbital mechanics, appeared and disappeared. And the rings were extraordinarily thin. If you scaled Saturn down to the size of a stadium, the rings would be thinner than a sheet of paper. Yet they stretched for hundreds of thousands of kilometers. Billions of individual particles, each one obeying orbital mechanics, independently, collectively producing the most visually striking structure in the solar system. Saturn's moon Titan presented yet another kind of surprise. It had been known since the 1940s to have an atmosphere, but Voyager found that atmosphere to be thicker than Earth's surface pressure, about 1.5 times what you would feel standing at sea level here. The surface was hidden beneath layers of orange photochemical haze. The atmosphere was dominated by nitrogen, like Earth's, but rich in methane and complex organic compounds. A full weather cycle, evaporation clouds, precipitation was operating, but with methane as the working fluid instead of water. Voyager 2 continued to Uranus in January of 1986 and Neptune in August of 1989. No spacecraft had ever been there. No spacecraft has been there since. Everything known today about the detailed structure of Uranus and Neptune, their atmospheric dynamics, their magnetic fields, the composition and character of their ring systems, the surface features of their moons, comes almost entirely from data collected during those two brief flybys. Combined, the time Voyager 2 spent in close proximity to each of these planets amounted to a matter of days. Two planets, largely unknown before and largely unvisited after, understood primarily through a single passing encounter nearly 4 decades ago. At Neptune, Voyager 2 found Triton, a moon orbiting in the opposite direction to Neptune's rotation, almost certainly a captured body from the outer solar system rather than something that formed alongside its planet. Triton's surface at -235 degrees Celsius is the coldest measured surface in the solar system. And yet, geysers erupt from it, jets of nitrogen gas driven not by internal heat but by sunlight, weak as it is at Neptune's distance, warming dark material beneath translucent nitrogen ice until the pressure beneath builds high enough to break through. The coldest surface in the solar system. Geysers powered by sunlight so faint it carries almost no energy. Some places refuse to behave the way they should. Of all the worlds Voyager visited, which one do you think is most likely to harbor life, and why? Those discoveries revolutionized astronomy. But they were only the opening act. When both spacecraft left the planets behind and pushed into the completely unexplored darkness, beyond what they encountered was not in any equation. After Neptune, everything familiar disappeared. No more planets ahead. No more moons to photograph, no more magnetic fields to map, no more atmospheres to sample. The last gravitational landmark in the solar system had been visited and left behind. What remained in front of both spacecraft was something no instrument had ever directly measured, no probe had ever entered, and no model had ever been tested against real data. Just the solar wind growing thinner and weaker with every passing year, and darkness deepening in every direction. The solar wind had been blowing outward from the sun continuously for 4.5 billion years, a constant stream of electrically charged particles, mostly protons and electrons, moving at between 300 and 800 kilometers per second, depending on solar activity. Near Earth, it was vigorous and well measured. By the time it reached the orbit of Neptune, roughly 30 astronomical units from the Sun, it had thinned considerably. By 50 astronomical units, thinner still. By 80 astronomical units, it was a shadow of what left the Sun, but it was still moving, still supersonic, and somewhere out in that darkness, it was going to hit something. The something it would hit had a name: the interstellar medium. The thin gas that fills the space between stars, not empty but extraordinarily close to it, roughly 1/10 of an atom per cubic centimeter. This gas exerts pressure, and as the solar wind travels farther from the Sun, its own pressure drops. At some point, the outward pressure of the solar wind and the inward pressure of the interstellar medium reach equilibrium. Before that equilibrium point, the models predicted something specific would happen. The solar wind was traveling faster than the speed at which pressure waves can propagate through the plasma itself, supersonic in the language of plasma physics. When supersonic flow encounters an obstacle, it cannot simply push aside, it doesn't slow gradually. It hits a threshold and drops suddenly, sharply, dramatically compressing, heating becoming denser almost instantaneously. This threshold has a name: the termination shock. Think of it like a spacecraft breaking the sound barrier but in reverse. Instead of something accelerating past a threshold and producing a shock wave behind it, here the solar wind is decelerating through a shock boundary, and everything changes on the other side. Velocity drops, density increases, temperature jumps. The plasma goes from moving in one direction at supersonic speed to something slower, hotter, and considerably more chaotic. Models predicted the termination shock would sit somewhere between 75 and 90 astronomical units from the Sun, a confident range based on the same plasma physics and interstellar density estimates that predicted the heliopore's location. The termination shock should come first, the heliopause some distance beyond it, with a turbulent transition region, the heliosheath filling the space between them. Voyager 1 reached the termination shock at 94 astronomical units, already beyond the predicted range, already suggesting the models were off. But the real strangeness wasn't the distance, it was the behavior. Voyager 1 didn't cross the termination shock once and leave it behind. It crossed it multiple times. The boundary moved. When the Sun became more active and produced stronger solar wind, the increased outward pressure pushed the termination shock farther from the Sun. When solar activity dropped, the shock moved back inward. This wasn't a slow drift over years, it was a dynamic oscillation, the boundaries surging outward and contracting back on timescales of months in response to individual solar events. Voyager 1, traveling outward at roughly 3.5 astronomical units per year, would cross the termination shock, enter the heliosheath, and then find the boundary expanding past it again, pulling it back into supersonic solar wind. Conditions. Then the boundary would contract, and Voyager would cross again. This happened repeatedly before the spacecraft finally stayed on the far side of the termination shock for good in December of 2004. A boundary that chases the spacecraft crossing it is not a boundary anyone had modeled. The termination shock in the existing literature was treated as relatively stable, moving slowly in response to the 11-year solar cycle, not oscillating fast enough to repeatedly overtake a spacecraft traveling at tens of thousands of kilometers per hour. Then came the second revelation from a different direction entirely. Voyager 2 encountered the termination shock on August 30th, 2007 at 84 astronomical units from the Sun, 10 astronomical units closer than where Voyager 1 had crossed it. Both spacecraft were moving outward. Both were measuring the same boundary around the same Sun. But Voyager 1 crossed at 94 astronomical units, and Voyager 2 crossed at 84, a difference of roughly 1.5 billion kilometers. If the heliosphere were a sphere, if it were symmetric in all directions as the models had assumed, both spacecraft should have crossed the termination shock at approximately the same distance from the Sun, regardless of which direction they were heading. The fact that they didn't was the first hard evidence, measured directly and unavoidably, that the heliosphere was not the symmetric bubble the models had drawn. Something was compressing it in some directions and extending it in others. The shape was wrong. The geometry assumed in decades of modeling didn't match the geometry of what was actually out there. Beyond the termination shock, both spacecraft entered the heliosheath, the region between the shock and the heliopause, where slowed, compressed solar plasma flows in a turbulent, disorganized way, trying to find a path around the obstacle of the interstellar medium pressing in from outside. The heliosheath was expected to be roughly 10 to 20 astronomical units thick, a transition zone, turbulent, yes, but governed by understandable physics, dominated by solar material, and bounded on the far side by the heliopause, the true outer boundary. What the heliosheath actually looked like from inside was more complicated. The magnetic field twisted and tangled. Plasma moved in unexpected directions. The transition was not clean, not orderly, and not well described by the models that had predicted it. And then in the year 2010, something happened that had no place in any prediction. Voyager, one still clearly inside the heliosheath, still surrounded by solar plasma, still registering magnetic field signatures characteristic of the Sun's field, began detecting a gradual but unmistakable increase in galactic cosmic point rays. High-energy particles from outside the solar system, accelerated by supernova remnants and other violent events across the galaxy. This should not have been happening. The heliosphere was supposed to act as a shield. Galactic cosmic rays should be low inside the heliosheath and jump sharply only at the heliopause, the outer boundary. A gradual increase well inside the heliosheath suggested the boundary wasn't a clean barrier at all. Something was letting galactic particles through before the official boundary had been reached. The edge was not a wall. It was permeable leaking, structured in ways the models had not anticipated. Then, in June of 2012, Voyager 1 found something stranger still. Moving through the heliosheath, the spacecraft entered a region where the magnetic field became unusually organized, not tangled and turbulent as the surrounding heliosheath had been, but aligned in a consistent direction. And along these ordered field lines, particles were flowing in both directions simultaneously. Solar particles streaming outward toward interstellar space, galactic cosmic rays streaming inward toward the Sun. On the same field lines, at the same time, it was a structure that connected the heliosheath directly to interstellar space, a channel through which particles from both sides could pass freely in both directions without requiring either side to have technically crossed the boundary separating them. No model had predicted this. No theoretical paper had described it. It had no name until Voyager found it, and then scientists called it the magnetic highway because that was the most accurate description of what it appeared to be. A highway, with traffic moving both ways. Voyager 1 spent roughly 2 months inside this structure before everything changed again. If the boundary of the solar system keeps moving and keeps letting things through, where does the solar system actually end? August of 2012, everything changed within a matter of days. Solar particles vanished. Cosmic rays surged. But the magnetic field did not do what everyone had been waiting for it to do, and that triggered the most intense scientific debate in the modern history of space physics. On August 25, 2012, the data coming back from Voyager 1 changed in a way that was impossible to ignore. Solar particles, the low-energy charged particles that originate from the Sun and had been Voyager's constant companion for 35 years, dropped to near zero within a matter of days. Not gradually, not slowly fading over weeks the way the models had suggested they might. They essentially vanished. At the same time, galactic cosmic rays, high-energy particles from sources outside the solar system, jumped to a new elevated level and stayed there steady and stable. These were the two classic signatures of heliopause crossing. The two things every model had predicted would happen when a spacecraft finally moved from the heliosheath into true interstellar space. Solar particles disappear. Galactic cosmic rays rise sharply. Both happened cleanly within days of each other. And yet the magnetic field did not rotate. Every model, every simulation, every theoretical paper describing what a heliopause crossing should look like had included a third signature, a change in the direction of the magnetic field. Inside the heliosphere, the Sun's magnetic field dominates, stretched, twisted, and wound into a spiral by the Sun's rotation over billions of years, but fundamentally solar in origin and direction. Outside the heliopause, the galactic magnetic field takes over a different field, with a different orientation reflecting the large-scale structure of the Milky Way rather than the Sun's rotation. When Voyager 1 crossed the boundary, the magnetic field should have rotated to reflect this transition. It didn't. It kept pointing in the same direction it had been pointing throughout the heliosheath. For a spacecraft that had just produced 2 out of 3 predicted crossing signatures, this was deeply confusing, and it split the scientific community straight down the middle. One group of scientists looked at the solar particle data and the cosmic ray data and said those are the signatures. The spacecraft has crossed the heliopause. The magnetic field will need to be explained separately. The other group looked at the magnetic field and said the field rotation is the most fundamental indicator of which plasma environment you're in. Without it, you cannot claim a crossing. Something else must explain the particle data, the same dataset. 2 opposing conclusions, both argued by serious, careful scientists with legitimate points. The debate ran for more than a year. Papers were published, counterpapers followed. Alternative explanations were proposed. Perhaps Voyager was in some previously unknown intermediate region, neither fully heliosheath nor fully interstellar space. Perhaps the heliopause had multiple structural layers. Perhaps the magnetic highway Voyager had detected months earlier was somehow responsible for the particle signatures without a true crossing having occurred. Meanwhile, Voyager 1 kept flying, 17 kilometers per second. Indifferent to the argument being conducted on its behalf back on Earth, in September of 2013, NASA made the official announcement Voyager 1 had crossed the heliopause on August 25, 2012. The spacecraft was at 121 astronomical units from the Sun, 20 to 30% farther than any model had predicted, more than 4 billion kilometers beyond where the boundary was supposed to be. The explanation for the magnetic field took longer to settle. Eventually, analysis showed that the local galactic magnetic field in the specific region where Voyager 1 happened to cross simply runs roughly parallel to the Sun's field at that location. A coincidence of geometry pure and unrepeatable. The two fields pointed in nearly the same direction, not because the physics had failed, but because the universe happened to arrange itself that way at that particular crossing point. No model had included this possibility, because no model could have anticipated it. You cannot predict a coincidence. The confirmation came with a second data point when Voyager 2 crossed the heliopause on November 5, 2018 at 119 astronomical units approaching from a different direction. This time a magnetic field rotation of approximately 20 degrees was measured, small but unambiguous. The two spacecraft crossing in different locations experienced different magnetic geometries, confirming that the field in nearby interstellar space is not uniform, that it varies from place to place, and that Voyager 1's crossing had genuinely been obscured by an unlikely alignment that happened to erase the expected signature. But the crossing story had one more chapter that nobody anticipated. The solar storm of 2012 produced pressure waves that traveled outward through the heliosphere at high speed. Those waves took 2 to 3 years to reach the heliopause. When they arrived, they pushed the boundary outward temporarily, expanding it beyond Voyager 1's position. The heliopause, in other words, moved past Voyager 1 after the spacecraft had already crossed it. For roughly 8 months after its confirmed crossing into interstellar space, Voyager 1 detected brief returns of solar particles, the boundary surging past it and briefly re-enclosing it, then contracting again and releasing it back into interstellar space. The heliopause didn't just move, it breathed, expanded and contracted in response to events at the Sun, with amplitudes large enough to swallow and release a spacecraft traveling at tens of thousands of kilometers per hour. The boundary of the solar system is not a line you cross once and leave behind. It is a dynamic region pulsing with the Sun's activity, potentially hundreds of millions of kilometers thick, permeable in both directions, and capable of moving faster than any spacecraft currently built can outrun. For more than a year, the greatest minds in space physics debated whether the spacecraft had made it out, while the spacecraft itself had no idea and no interest, quietly continuing at 17 kilometers per second. If the boundary is both moving and permeable, do inside and outside the solar system still mean anything? Once past the heliopause, Voyager placed its instruments into true interstellar space for the first time, and the numbers it sent back looked nothing like any page in any textbook, in ways nobody had expected. Every measurement ever made of interstellar space before Voyager was indirect. Telescopes collected light that had traveled across vast distances, passed through interstellar gas, and arrived carrying spectral fingerprints of the material it had moved through. Radio telescopes detected emissions from hydrogen clouds hundreds of light years away. Theoretical models built their predictions on this accumulated remote data, carefully analyzed and cross-referenced across decades of astronomy. It was rigorous work, conducted by skilled scientists, using the best available methods. But there is a fundamental difference between measuring how light behaves after traveling through something and putting an actual physical instrument inside that something and reading what it says directly. In August of 2012, humanity did the second thing for the first time. The density of the interstellar medium, measured directly by Voyager's instruments, came in at approximately 0.08 particles per cubic centimeter. That number requires a moment to sit with. The best vacuum chambers, built in laboratories on Earth, precision facilities used for physics experiments requiring the lowest possible background particle count, achieve densities of around 1 million particles per cubic centimeter. The interstellar medium is more than 10 million times less dense than the best vacuum humans have ever manufactured, and yet it is not nothing. 0.08 particles per cubic centimeter means roughly 80,000 particles in every cubic meter. If you could stand in interstellar space, which you cannot for reasons that will become clear shortly, and reach out your hand, the average distance between individual particles around you would be more than 2 centimeters. Your entire body would contain perhaps a few billion interstellar particles at any given moment, spread so thinly that none of them would interact with you in any meaningful way. Scale that up to the galaxy, however. Multiply those 80,000 particles per cubic meter across the hundreds of billions of cubic light-years that fill the Milky Way, and the total mass of the interstellar medium becomes enormous, comparable in total to the mass of all the stars in the galaxy combined. Individually negligible, collectively staggering. The temperature reading was perhaps the most counterintuitive number Voyager returned. Instruments measured the temperature of the interstellar medium at somewhere between 54,000 and 90,000 degrees Celsius. By any everyday standard, that sounds extraordinarily hot, hotter than the surface of the sun, hot enough to instantly vaporize any material known. But a human being placed in interstellar space would not burn. They would freeze, Temperature in the physics of thin gases measures the average kinetic energy of individual particles, how fast they are moving, not how much heat they can transfer to something else. Heat transfer requires collisions. Collisions require particles to be close enough to interact. In the interstellar medium, particles are so far apart that they almost never collide with anything. A thermometer placed in interstellar space would lose heat to its surroundings through radiation far faster than the sparse particles around it could transfer energy back. The net result would be cooling, not heating. The temperature is real. The danger it implies is not. The two facts coexist without contradiction, which is part of what makes interstellar space so difficult to reason about using ordinary intuition. The pressure measurement was the one that put everything in perspective. Voyager measured the pressure of the interstellar medium at approximately 0.00000003 Pascal. Written out fully, that is 3 billionths of a Pascal. Earth's atmospheric pressure at sea level is approximately 101,000 pascals. The interstellar medium exerts a pressure roughly 30 trillion times smaller than the air pushing against you right now as you read this. That pressure, that almost incomprehensibly small force, is precisely what stopped the solar wind. A wind that has been blowing outward from the sun at hundreds of kilometers per second for 4.5 billion years, streaming plasma across 10 billion kilometers of space in every direction, was brought to a halt by a pressure that a household vacuum cleaner would barely notice. The balance point between these two forces is the heliopause. And the interstellar medium side of that balance is 3 billionths of a Pascal. Scale and force work differently in space than intuition suggests. That more than any single measurement is what Voyager's direct readings made undeniable. Voyager 2 measured the interstellar magnetic field at approximately 50 nanotesla. Earth's magnetic field at the surface registers around 50,000 nanotesla, roughly 1 million times stronger. The interstellar field is almost unimaginably weak by any terrestrial reference point, but it extends across thousands of light years without interruption. Its total energy integrated across those distances is not small. It shapes the trajectories of charged particles across the entire galaxy. It connects stellar systems through field lines that stretch between them across the void, weak, locally, consequential, cosmically. Every one of these measured values differed from what the models had predicted. Not by enormous factors, the basic picture was right. The interstellar medium was thin and cold in the way that mattered, and hot in the way that didn't. The magnetic field was weak. The pressure was tiny. But the specific numbers were off. The density was somewhat lower than the estimates built from remote astronomical observations, and that downward discrepancy, modest as it was turned out to be, the primary reason the heliopause sat 20 to 30% farther from the pause sun than predicted. A small input error in the density estimate produced a large output error in the location of the balance point. The math was correct. The data going into the math was not quite right. The difference between those two things is billions of kilometers. Beyond the individual measurements, Voyager revealed something structurally important. The interstellar medium is not uniform. Density and magnetic field strength vary by 10 to 20% across distances of a few astronomical units. The space between stars is not a smooth, featureless medium that models can represent with a single set of average values. It has texture variation structure at scales that remote observation cannot resolve. The space between stars is more complex than anything anyone had imagined, and we had been imagining it for a very long time. If interstellar space is more sparse than the best artificial vacuum humans have ever created, does a true perfect vacuum actually exist anywhere in the universe? But the strangest discovery was not what Voyager measured in interstellar space. It was what it found, traveling through it. The invisible, the hand of the sun reaching past the boundary in a way nobody thought was possible. In October and November of 2012, Voyager 1's plasma wave instrument detected something that had no place in any model of interstellar space: oscillations. waves of compression and rarefaction moving through the plasma around the spacecraft. Not the kind of disturbance you would expect from the solar wind. The solar wind doesn't reach interstellar space contained as it is within the heliosphere. What Voyager was detecting was different. These were pressure waves propagating through the interstellar medium itself, traveling through the gas between the stars like sound travels through air, carrying energy from a source that by all prior understanding should have had no way of sending anything past the heliopause. The waves were real. The instruments were functioning correctly. And when scientists worked backward through the physics to trace where they had come from, the answer was unambiguous. A coronal mass ejection from the Sun in 2012, a powerful eruption that hurled billions of tons of solar plasma outward through the heliosphere, had generated a pressure pulse. That pulse traveled through the heliosphere at high speed, reached the heliopause, and instead of simply stopping at the boundary, transmitted its energy into the interstellar medium on the other side, launching a shockwave that continued, propagating outward through interstellar space. By the time Voyager 1 detected it, the wave had already crossed the heliopause and traveled a meaningful distance beyond it. The Sun had reached past its own boundary. Not with particles, the solar wind stays inside the heliosphere, but with pressure, with waves, with disturbances that carry the Sun's activity outward into space that was supposed to be beyond its influence entirely. Over the following years, Voyager 1 detected 3 more such waves in 2013, 2014, and 2015. Each one was traced back to a specific solar event years earlier. A storm erupts on the Sun. Its pressure pulse travels outward through 10 billion kilometers of heliosphere, crosses the heliopause, and continues propagating through interstellar space at roughly 60 kilometers per second, far slower than the solar wind, but fast, enough to cover several astronomical units in a year, and reach Voyager's instruments with enough energy to register clearly. None of this had been predicted. The expectation was that the heliopause was a one-way filter in this respect. Solar particles stay inside, galactic particles stay outside, and the boundary ends the Sun's dynamic influence. What Voyager found was that the boundary transmits pressure. The Sun's most energetic outbursts echo into interstellar space as shock waves that propagate for unknown distances before finally dissipating. The practical value of these detections extended beyond the discovery itself. The frequency of the plasma oscillations Voyager measured allowed scientists to calculate the local electron density of the interstellar medium with high precision, a measurement that remote observation from Earth could not have achieved. A wave's oscillation frequency in a plasma depends directly on the density of free electrons around it. By reading the frequency, Voyager's instruments effectively performed an in situ density measurement without requiring a dedicated density probe. A method of extraordinary subtlety carried out from billions of kilometers away by instruments designed in the early 1970s. The Sun's long reach into interstellar space also carries a broader implication that scales upward to the entire galaxy. Every star with a heliosphere, and most stars have one sustained by their own stellar wind, produces the same effect. Every coronal mass ejection from every star sends pressure pulses into the interstellar medium around it. The space between stars, rather than being the passive, featureless void it was once imagined to be, is threaded continuously with shock waves from billions of stellar sources overlapping, interacting, propagating through the medium at various speeds and frequencies. Interstellar space is not quiet. It never was. We simply had no instrument inside it until 2012 to hear what was already there. The galactic magnetic field, measured by both Voyager spacecraft as they crossed into interstellar space, produced its own set of surprises. Voyager 1's crossing, as described earlier, showed almost no change in magnetic field direction, the local galactic field happening to align with the Sun's field at that particular location. A geometric coincidence that confused the crossing confirmation for more than a year. But beyond the crossing itself, the field measurements in interstellar space revealed something structurally important. Voyager 2, crossing at 119, astronomical units in a different direction measured a field rotation of approximately 20 degrees from what Voyager 1 had measured. The two crossing points are separated by more than 100 astronomical units, a vast distance by any solar system standard. And the magnetic field at those 2 points points in measurably different directions. This means the galactic magnetic field in the region immediately surrounding the solar system is not uniform. It varies in direction and presumably in strength across distances comparable to the size of the heliosphere itself. The field is structured, wound, and bent by the cumulative effects of stellar winds, supernova remnants, and plasma currents operating over millions of years across the local region of the galaxy. 2 data points separated by over 100 astronomical units are enough to confirm this variation, but nowhere near enough to map it. The galactic magnetic field matters because it governs how cosmic rays move. Charged particles spiral along magnetic field lines as they travel. Field orientation determines which directions cosmic rays can approach from efficiently and which directions are effectively blocked. Understandable field structure is essential to understanding the radiation environment of the solar system, and Voyager has given us exactly 2 measurements of it at 2 specific locations, with everything in between unknown. Cosmic ray intensity in interstellar space, as measured by both spacecraft after crossing the heliopause, rose by roughly 10 to 20% compared to levels in the heliosheath. The heliosphere provides meaningful shielding even in its outermost layers, a fact confirmed directly for the first time by Voyager's measurements. But the directionality of the cosmic rays was not what anyone expected. Galactic cosmic rays arrive preferentially from certain directions and less abundantly from others. The distribution is not uniform. There are enhancements from specific directions and deficits from others, creating an anisotropy, a directional structure to the cosmic ray environment that reflects the actual source distribution and propagation history of these particles through the galaxy. The most striking deficit was from the direction of the galactic center. This is counterintuitive. The galactic center is the most densely populated region of the Milky Way, the highest concentration of stars, the highest rate of supernovae, the most prolific production of the high-energy particles that become cosmic rays. By naive expectation, cosmic rays should arrive most abundantly from that direction. Instead, Voyager measured fewer cosmic rays arriving from the galactic center than from the outer regions of the galaxy. The explanation lies in the galactic magnetic field. The field is stronger in the inner galaxy, closer to the center. Cosmic rays produced in the central regions spiral along field lines and scatter repeatedly off magnetic irregularities before they can travel outward. The denser, stronger field of the inner galaxy acts as a trap containing and redirecting particles rather than letting them stream freely outward. Fewer particles escape to the outer galaxy from the center than are produced there, and the imbalance shows up directly in Voyager's measurements of which directions the cosmic rays come from. If cosmic rays influence atmospheric chemistry and may affect climate, could the sun's changing position in the galaxy over millions of years have played a role in Earth's ice ages? 7 discoveries. 7 times reality beat the theory. But the real question is not where we went wrong, it is what Voyager found that tells us about the future of humanity in the universe. Every diagram of the solar system ever drawn for a textbook placed the heliosphere as a sphere, a bubble roughly symmetrical in all directions, centered on the sun with the heliopause as its outer skin at a more or less consistent distance. Regardless of which direction you measured, the Voyager data made that diagram obsolete. Voyager 1 crossed the heliopause at 121 astronomical units, heading in a direction that corresponds roughly to the nose of the heliosphere, the direction the sun is moving through the interstellar medium. Voyager 2 crossed at 119 astronomical units, heading in a different direction more toward the flank. The crossing distances were close to each other, which initially might seem to support rough symmetry. But the similarity in distance obscures the deeper asymmetry that both crossings reveal when analyzed together. The heliosphere is not a sphere. Its true shape is closer to a bullet or a teardrop, a form dictated not by the sun's output alone, but by its motion through the interstellar medium. The solar system is not stationary. The entire system, sun, planets, moons, comets, asteroids, and the heliosphere that encloses them, moves through the local interstellar medium at approximately 26 kilometers per second. That motion has been continuous for the sun's entire 4.5 billion year existence. And like any object moving through a fluid medium, it creates a directional asymmetry. The nose of the heliosphere, the direction the sun is moving into, faces a headwind. The interstellar medium presses harder against the nose than against the sides or the tail. This compression pushes the heliopause closer to the sun at the nose, creating the blunt forward face of the bullet shape. The sides are less compressed. And behind the sun, in the direction of travel's wake, the heliosphere stretches outward into a tail that extends for distances nobody has yet measured directly. Some theoretical models suggest the heliotail extends for hundreds of astronomical units. Others suggest it may be even longer, potentially reaching thousands of astronomical units before the solar wind material finally disperses completely into the surrounding interstellar medium. No spacecraft has ever traveled in that direction to find out. The tail of our own cosmic home remains unmapped, its true length unknown. The same uncertainty surrounds a predicted structure called the bow shock, a shock wave in the interstellar medium itself, formed ahead of the heliosphere as the solar system moves through the galaxy. Models have placed it somewhere between 140 and 230 astronomical units from the Sun. But given how wrong those same models were about the heliopause location, the bow shock could be anywhere in that range, or well beyond it. Neither Voyager has traveled far enough in the right direction to find it. Whether it exists at all in the classical sense remains an open question. The shape of the heliosphere matters in ways that extend directly to conditions on Earth. Cosmic rays approach the solar system from all directions, but a heliosphere, shaped like a bullet rather than a sphere, offers different levels of protection in different directions. The compressed nose provides less shielding depth than the extended tail. The flanks occupy an intermediate position. A cosmic ray approaching from the nose direction encounters less heliosphere to traverse before reaching the inner solar system than one approaching from behind. The asymmetric shape creates an asymmetric shield, and the radiation environment of the inner solar system is shaped accordingly. This is not an abstract concern. Cosmic rays affect the upper atmosphere. They produce cosmogenic isotopes, carbon-14, beryllium-10, chlorine-36, that leave measurable traces in ice cores, ocean sediments, and tree rings going back hundreds of thousands of years. The record of cosmic ray flux on Earth, written in these isotope ratios, reflects variations in the heliosphere's shielding capacity over geological time. The shielding capacity is not constant because the heliosphere itself is not constant. Its size and shape change with the environment the Sun moves through, and right now the Sun is moving through a region of the interstellar medium called the local interstellar cloud, a slightly denser than average patch of gas, a few light years across. This denser surrounding medium pushes harder against the heliosphere from all directions, compressing it relative to what it would be in a less dense environment. In a few thousand years, the Sun will exit this cloud and enter a region of lower density. When that happens, the reduced external pressure will allow the heliosphere to expand, growing larger, extending its boundaries outward, changing its shape as the balance between solar wind and interstellar medium shifts to a new equilibrium. The heliosphere that Voyager measured is a snapshot of one particular configuration, valid for this moment in the Sun's 4 billion year journey through the galaxy. Over millions of years, the Sun has moved through regions of varying interstellar density. Each transition changed the heliosphere's size and shape. Each change in size and shape altered how much cosmic radiation reached the inner solar system. And those variations in cosmic ray flux left traces in atmospheric chemistry, in isotope ratios, in climate proxies, preserved in ancient rock and ice. Whether those changes were large enough to influence Earth's climate significantly remains a subject of active research. The connection between cosmic ray flux and cloud formation, and between cloud formation and global temperature, is not fully established. But the physical chain, from interstellar environment to heliosphere, shape to cosmic ray penetration to Earth's atmosphere, is real, measurable, and longer in reach than most people have imagined. The heliosphere is not a fixed structure surrounding a stationary sun. It is a dynamic envelope around a moving star, shaped by everything the star encounters on its journey through the galaxy, leaving its signature on the planet that travels inside it. If our heliosphere is constantly changing shape and size in response to its surroundings, is the solar system a stable entity, or something that is continuously transforming? 7 shocks, 7 times, the universe refused to follow our equations. But there is a larger question than all of them. What are those 2 spacecraft actually carrying, and why might it be the most meaningful thing humanity has ever made, even though nobody may ever be able to read it? On February 14, 1990, mission controllers sent a command to Voyager, one by then already far beyond Neptune's orbit, heading outward toward the heliopause, still decades away. The command instructed the spacecraft to turn its camera backward toward the inner solar system it had left behind 13 years earlier. The resulting image became one of the most discussed photographs in human history. Earth appeared as a pale blue dot, not even a full pixel in size, suspended in a band of scattered sunlight that crossed the frame like a thin golden ray. No continents were visible, no oceans, no sign of the 7 billion people living on its surface, building cities, fighting wars, falling in love, writing music, burying their dead. Just a point of faint blue light, smaller than a dust mote, lost in the immensity of space. Carl Sagan, who had been one of the driving forces behind the decision to take that photograph, looked at it and wrote words that have been repeated so many times since that they risk losing their weight. Every king who ever ruled, he observed, every war ever fought, every empire that rose and fell, every act of cruelty and every act of kindness in the entire recorded span of human existence, all of it happened on that dot, that single sub-pixel point of blue, that mote of dust suspended in a sunbeam. The scale of what the image communicated was not comfortable. It was not meant to be. But Voyager 1 was carrying something that the pale blue dot image alone could not convey, something attached to its body before it ever left Earth, designed to outlast the spacecraft itself by an incomprehensible margin of time. A golden record, 12 inches in diameter, gold-plated copper, encoded with sounds and images from the planet that made it. The golden record is easy to describe superficially. Music from many cultures, greetings in 55 languages, sounds of Earth 116 images. But the description misses what the object actually represents. It is the answer to a question that no civilization had ever seriously attempted to answer before. If you had one chance, a single, unrepeatable opportunity to tell another intelligent civilization that you exist, what would you say, not what you would want them to admire, not what you would want them to fear? What would you say if you had to compress the entire reality of human existence into something that could fit on one disk, survive for billions of years, and be understood by minds shaped by completely different evolutionary pressures on completely different worlds? The committee, tasked with creating the record, found that answering this question was far harder than anyone had anticipated. The selection process was contentious in ways that revealed something important about what humanity actually is. Who decides what represents everyone? Which music? Western classical music dominated the early proposals: Bach, Beethoven, Mozart, because these were the traditions most familiar to the committee members. But the committee understood that a record claiming to represent humanity, while drawing primarily from one cultural tradition, was not representing humanity. It was representing a fraction of it dressed up as the whole. Traditional music was sought from Java, from Senegal, from the Australian Aboriginal tradition, from Peru, from Japan, from India, from Azerbaijan. Blues from the American South, jazz, Chuck Berry's guitar, Georgian choir music, with its dense polyphonic texture. Each edition opened a debate: who was being included, who was being left out, and on what authority was anyone making these decisions. Religious music raised the same problem at higher stakes. Include hymns from one tradition, and you implicitly elevate it. Include from many and you run out of space. Include none and you erase one of the most universal aspects of human experience from the record entirely. The images generated their own controversies. Some committee members argued for including images of war, poverty, and suffering, the full range of human reality, not just the aspirational version. Others argued that the record should represent what humanity was reaching toward, not just what it had been. The final selection landed somewhere between these positions, emphasizing human achievement and natural beauty, while acknowledging the complexity of existence without dwelling on its darkest expressions. The committee debated for months over whether to include anatomically accurate images of the human body. The argument for inclusion was straightforward: any civilization capable of finding the record would need to understand what made it. Hiding basic biological structure would be a strange kind of modesty. The committee decided the image should be included. Encoded on the record's aluminum cover, etched in a way that requires no knowledge of any human language to interpret, is a pulsar map. 14 pulsars, rotating neutron stars that emit radio pulses at frequencies as unique as fingerprints, are represented with lines extending from a central point, each line's length proportional to the pulsar's distance from the dim sun, each annotated with the pulsar's precise period. Pulses slow down over time as they lose energy at rates that can be calculated. A civilization that finds the record and can identify the pulsars on the map, which any civilization capable of interstellar travel almost certainly could, can use the map to locate Earth in the galaxy and determine when the record was made, accurate to within a small fraction of the sun's lifetime. It is a message in a bottle that includes return address instructions, in a language that needs no translation, the language of physics. Gold does not corrode. In the vacuum of space, with no oxygen and no moisture, the record's surface will remain intact for timescales that make every human monument look momentary. The pyramids of Giza will be gone. The Great Wall will be rubble. Every book ever written will have crumbled. Every digital record humanity has ever created will have become unreadable. The sun itself will have exhausted its hydrogen fuel, expanded into a red giant, and collapsed into a white dwarf, and the golden record will still be there, orbiting the galactic center alongside the cold remains of the solar system, its grooves intact, its information preserved, waiting. The probability that it will ever be found is, in honest assessment, almost zero. Space is too vast. The spacecraft is too small. It is not aimed at any particular star. The chance that it passes close enough to any inhabited system at a time when that system contains a civilization capable of recognizing and recovering it within a time frame of billions of years, the mathematics of this are not encouraging. But the probability of being found was never really the point. The point was the question the record forced humanity to answer. For the first time in its history, a species sat down and tried to decide seriously and without easy answers who it was and what it wanted to be remembered for. The arguments, the compromises, the inclusions and exclusions, all of it was a mirror held up to humanity at a particular moment in its existence. What looked back was complicated, incomplete, and genuinely human. The committee debated for months over whether to include images of the naked human body, and ultimately decided yes on the grounds that introducing the human species to another civilization while concealing its most fundamental biological structure would be a peculiar kind of omission. If today you could choose one single thing to represent humanity and send it into the universe, what would you choose? The golden record will still be there billions of years from now, but the spacecraft carrying it is dying in ways that are teaching 21st century engineers lessons they could not have learned anywhere else. In the year 2026, Voyager 1 has approximately 249 watts of electrical power remaining. The spacecraft requires approximately 245 watts to keep its essential systems running: instruments, computers, transmitters, and the heaters that prevent critical components from freezing in the cold of deep space. The margin between available power and required power is 4 watts, less than what a small LED desk lamp consumes. And that margin is shrinking by roughly 4 watts every year as the plutonium-238 in the radioisotope thermoelectric generators continues its irreversible decay. There is no way to slow this process, no way to add power, no way to trade off against it. Every year the budget drops by 4 watts permanently, and the team managing the spacecraft must decide what to turn off next. Each of those decisions is made under a constraint that has no parallel in any other engineering environment on Earth. When mission controllers in Pasadena, California, send a command to Voyager 1, the signal travels at the speed of light, the fastest anything in the universe can travel, and still takes more than 22 hours to reach the controller, spacecraft. The confirmation that the command was received and executed takes another 22 hours to return. A single command sent and acknowledged consumes more than 44 hours of calendar time before the engineers know whether it worked. There is no debugging in real time. There is no trying something and checking the result immediately. Every action is a commitment made in advance with a 2-day wait before any feedback arrives. If a command has an error, the consequences play out alone, billions of kilometers from anyone who could intervene for nearly 2 days before the problem is even detected. This is the environment in which the Voyager team works every day, managing hardware approaching 50 years of age across distances that light itself takes nearly a full day to cross. In 2020, mission controllers made the decision to turn off the heater for Voyager 2's cosmic ray instrument. The heater had been consuming power the spacecraft could no longer afford to spare. Without it, the instrument's temperature dropped to 59 degrees Celsius, below the lower limit of its design specification. Below the temperature range it was certified to operate within. Below anything the engineers who built it in the early 1970s had intended it to experience. The instrument continued working normally. Components designed and manufactured more than 4 decades earlier, running at temperatures nobody designed them for, in an environment no laboratory can replicate, continued returning valid scientific data. The philosophy of over-engineering building components, rated for loads beyond what the mission required, choosing simplicity over elegance, designing redundancy into everything that mattered, had produced robustness that outlasted not just the mission's design lifetime, but the expectations of everyone involved in building the spacecraft. In 2023, something went wrong with Voyager 1 in a way that had never happened before. A memory chip in the flight data system, one of the 3 computer systems managing the spacecraft, developed a fault. The chip controlled a small section of memory used to store the instructions for formatting science and engineering data before transmission. When the fault developed, the affected memory began producing corrupted output. The spacecraft continued operating normally by every other measure, but the data stream arriving at Earth was garbled, unreadable, mixed with patterns that made no sense. Diagnosing the problem took weeks, analyzing the corrupted data from 22 light hours away, working out what the fault pattern implied about the hardware, determining which part of the memory was affected and how. Once the fault was localized, engineers designed a software patch that would route the spacecraft's data formatting around the damaged memory section, using other parts of the available memory instead. The patch had to work correctly the first time. There was no testing it on the actual hardware before deploying it. The patch was uploaded to Voyager 1. Engineers waited 45 hours for the command to arrive, execute, and return a confirmation. When the confirmation came back, the data stream was clean. The fix had worked. Debugging software that is 50 years old, running on hardware that cannot be touched, 22 light hours away from the nearest person who can help. There is nothing else in the history of engineering that resembles this. The end, when it comes, will be quiet. Sometime between 2030 and 2032, the power budget of the Voyager spacecraft will fall below the threshold needed to operate the transmitters alongside any science instruments. Engineers will face a final series of decisions about what to shut down and in what order, trying to preserve the last useful measurements as long as possible before the transmitter itself must be sacrificed to keep some other system alive, or until there is simply not enough power for any of calm. The last signal will fade into background noise. The deep space network will listen for a while longer in case something unexpected comes through. And then there will be silence from those 2 points in the sky that have been transmitting continuously since the summer of 1977. But the spacecraft will not stop. With no friction in space to slow them both, Voyagers will continue at their current velocities indefinitely. Voyager 1 will keep traveling at approximately 17 kilometers per second relative to the Sun, not accelerating, not decelerating, just moving year after year, decade after decade, century after century. In approximately 300 years, Voyager 1 will reach the inner edge of the Oort cloud, the vast diffuse shell of icy bodies surrounding the solar system, at distances ranging from roughly 2,000 to 100,000 astronomical units. It will spend thousands of years crossing through it. In approximately 30,000 years, it will finally pass beyond the outer edge of the Oort cloud and leave the Sun's gravitational sphere of influence entirely. In approximately 40,000 years, it will make its closest approach to the star Gliese 445, passing within 1.6 light-years of it. Not close enough to enter that star's planetary system if it has one. Not close enough for any gravitational interaction. Just drifting past in the darkness between stars carrying its golden record and its silent instruments, unreachable and unmaintained, still intact. 1.6 light-years is approximately 15 trillion kilometers. That is the definition of a near miss in interstellar terms. When Voyager finally goes silent for the last time, is that the end of the mission or simply the beginning of a phase we are no longer part of? Voyager is fading, but what it leaves behind is shaping what comes after it, a more ambitious mission, faster and farther, carrying questions that no living generation will survive long enough to hear answered. Voyager answered questions nobody had thought to ask. It also left behind questions nobody had thought to formulate, because nobody knew those questions existed until Voyager's data made them visible. That is the nature of genuine exploration. You don't know what you don't know until something goes out there and comes back with information that doesn't fit what you thought you understood. Voyager went out. It came back with decades of data. And scattered throughout that data were gaps, anomalies, and half-answered puzzles that now define the frontier of heliospheric science. What happens next depends on whether humanity is willing to make a commitment that will outlast everyone currently alive. NASA's Interstellar Probe is a mission concept currently in development, not yet approved, not yet funded for full construction, but studied in serious scientific and engineering detail. The goal is to reach between 500 and 1,000 astronomical units from the Sun within 50 years of launch. To put that in perspective, Voyager 1 has covered approximately 160 astronomical units in nearly 50 years. The interstellar probe would need to travel 3 to 6 times farther in the same time. That requires traveling at roughly twice Voyager's speed, or faster. Achieving that velocity with a conventional rocket trajectory, the way Voyager used planetary gravity assists to build speed, is not feasible with current technology. The planetary alignment that gave Voyager its velocity won't repeat in a useful configuration for this purpose. A different approach is needed. The concept under study involves a close solar flyby, approaching the Sun more closely than any spacecraft has ever deliberately done, combined with a solar sail or solar thermal propulsion system that uses the intense energy at close solar distances to accelerate the spacecraft to the required speed. The physics are real. The engineering challenges are significant. Getting a spacecraft close enough to the Sun to harness that energy without destroying it in the process requires materials and thermal management capabilities that push the boundaries of what currently exists. But the mission is designed around 21st century instruments, not 1970s technology. If it launches, it will carry detectors, magnetometers, plasma analyzers, and imaging systems with sensitivity and resolution that Voyager's builders could not have imagined. Everything Voyager measured the interstellar probe would measure with far greater precision, and it would measure things Voyager couldn't measure at all. The questions left open by Voyager are specific and significant. The heliotail, the extended wake of the heliosphere stretching behind the Sun's direction of travel, has never been directly explored. Models suggest it may extend for hundreds or even thousands of astronomical units before the solar wind material finally mixes completely with the surrounding interstellar medium. No spacecraft has traveled in that direction at sufficient distance to find out. The actual length and structure of the tail remain unknown, estimated from models that have already proven themselves unreliable about the heliosphere's other dimensions. The bow shock, the predicted shock wave in the interstellar medium ahead of the heliosphere formed by the solar system's motion through the local interstellar cloud, has not been confirmed to exist at the location models place it. Between 140 and 230 astronomical units. Given that the heliopause itself was found more than 20 astronomical units beyond its predicted location, the bow shock could be anywhere in that range, or substantially farther. It may not exist in the classical sense at all, depending on the local interstellar conditions. An interstellar probe, traveling in the right direction, could settle this question within its operational lifetime. Beyond the heliopause, the interstellar medium's properties, measured by Voyager at approximately 120 astronomical units, represent a single set of data points at a single distance. Whether those properties, the density, the magnetic field, strength and direction, the temperature, the cosmic ray flux, remain constant at greater distances or change significantly, is unknown. The local interstellar cloud the Sun is currently moving through extends for a few light-years in various directions. What lies beyond its edge, and how the transition between cloud boundaries affects the environment around the solar system, has never been measured. The interstellar probe, if it reaches 500 to 1,000 astronomical units, would cross multiple interstellar cloud boundaries and measure the medium across a range of distances and environments that Voyager never reached. The picture it would return would be fundamentally more complete than anything currently available. But the interstellar probe's target distances, ambitious as they are, still represent a vanishingly small step toward what would constitute actual interstellar travel between star systems, rather than merely travel into the space between them. Proxima Centauri, the nearest star to the Sun, lies at 4.24 light-years. Converting that to astronomical units produces a number 268,000 astronomical units that strips away any comfortable sense of scale. At Voyager, one's current speed reaching Proxima Centauri would take approximately 73,000 years. That is 7 times longer than the entire history of human agriculture, longer than the time since the last ice age ended, longer than the existence of any continuous human civilization. Every institution, every language, every nation, every tradition that exists on Earth today would be unrecognizable long before a Voyager-speed spacecraft reached the nearest star. And Voyager 1 is not even traveling toward Proxima Centauri. It is heading in a different direction entirely. The closest stellar approach in its trajectory to the star Gliese 445 in approximately 40,000 years will still leave it 1.6 light-years away from that star at its nearest point. To reach another star system in a time frame that has any meaning for human civilization, decades rather than geological epochs, a spacecraft would need to travel at a minimum of roughly 10% of the speed of light. That is approximately 30,000 kilometers per second. Voyager 1's current speed is about 17 kilometers per second. 10% of light speed is approximately 1,700 times faster. No propulsion system that currently exists can achieve this. Theoretical proposals, laser sail systems, nuclear pulse propulsion, antimatter drives, each face engineering challenges that range from extremely difficult to currently impossible. But the physical barrier is real in a different way than the engineering barrier. Even if the propulsion problem was solved, a spacecraft traveling at 10% of light speed through the interstellar medium would face a continuous bombardment by the hydrogen atoms that fill that medium. At Voyager's speed, a hydrogen atom encountered along the flight path delivers negligible energy on impact. At 10% of light speed, every hydrogen atom becomes a high-energy projectile. The kinetic energy of each impact increases with the square of velocity, meaning it scales by a factor of nearly 3 million compared to Voyager's encounters with the same atoms. A spacecraft with 1 square meter of cross-section, traveling at 10% of light speed, would collide with roughly 100 trillion hydrogen atoms per second. The cumulative energy deposited in the hull material would be measured in kilowatts continuously for decades of travel. The erosion, heating, and radiation damage to any known material under those conditions over the duration of an interstellar voyage remains an unsolved engineering problem. Voyager's measurements of the interstellar medium's density, 0.08 particles per cubic centimeter, are the baseline data for calculating exactly how severe this problem is. The number seems impossibly small. At interstellar cruise velocities, it is not small enough. The Oort cloud adds another dimension to the scale of what lies between stars. Voyager 1 will reach the inner edge of the Oort cloud in roughly 300 years after its transmitters have been silent for nearly 3 centuries. The outer edge of the Oort cloud lies at approximately 100,000 astronomical units from the Sun. Exiting it entirely will take Voyager 1 approximately 30,000 years. For the full duration of that passage, 300 years from now, until 30,000 years from now, the spacecraft will technically still be within the Sun's gravitational sphere of influence, moving through a region populated by the most distant cometary objects in the solar system. The solar system, fully defined, extends far beyond the heliopause, far beyond where Voyager currently travels. Humanity's most distant artifact, after nearly 50 years of continuous flight, has crossed only the boundary of the Sun's plasma influence, not the boundary of its gravity. The true edge of the solar system is thousands of times farther than where Voyager 1 sits today. The scientists and engineers currently designing the interstellar probe understand something that requires a particular kind of acceptance. They will not live to see the mission's most important results. If the probe launches in the 2030s and reaches 500 astronomical units 50 years later, that places the primary data return in the 2080s. The researchers leading the concept studies today would be in their 80s or 90s if they are still alive at all. This is not unprecedented in science. Particle physics experiments are designed for decades of operation. Astronomical observatories are built for generations of users, but it is rare. The deliberate undertaking of a project whose primary scientific return will arrive after the people who conceived it are gone requires a form of institutional and generational commitment that most human endeavors do not demand. Voyager itself was this kind of project. The engineers who built it in the 1970s knew that its most distant discoveries would come long after they had retired. Some of them did not live to see the heliopause crossing confirmed. The data they made possible arrived at desks occupied by people who were children when the spacecraft launched. This is how science works across the distances of the solar system. And it is how it will have to work across the distances between stars, on timescales even longer, requiring commitments even more deliberate. Voyager did not answer everything. It was never going to. A single pair of spacecraft, traveling along 2 specific trajectories, measuring what their aging instruments could detect the data they returned, was extraordinary but finite. The questions they left open are in some ways more valuable than the answers they provided. Because the open questions are specific now, defined, pointed at particular distances, particular directions, particular phenomena that a better-equipped successor could actually address. What Voyager proved more durably than any single measurement is that the only way to actually know something about a place is to go there. Models built from remote observations are essential starting points. They are not substitutes for presence. The interstellar medium is what it is, not what the equations predicted. The heliopause is where it is not, where the simulations placed it. The shape of the heliosphere is what it actually is, not the convenient sphere that fit the mathematics neatly. Sending something out, waiting with patience that spans decades, and being willing to face results that overturn everything you thought you knew, that is the only honest method available. There is no shortcut. There is no model sophisticated enough to eliminate the need for the spacecraft. If humanity manages to send a spacecraft to another star system within the next 200 years, what do you think will surprise us most when it arrives? Voyager 1 is still flying, right now, at this exact moment as you read this, adding 17 kilometers to its distance from the Sun every second, quietly, without fatigue. Carrying the music of Bach, the sound of ocean waves, greetings in 55 languages, moving into darkness that has no map, no destination, and no one waiting at the other end. And exactly that is the most honest definition of exploration there is.